Welcome back. Time to get seated. Everyone knows 2 30-minute talk in the afternoon. First of which is by Rekha Santhanam.
Thank you. Thank you for the organizers for giving me this opportunity. It's kind of nice to be here and learn about so many things, meet new people, and realize that I haven't met people in decades, which is not a good thing. But, all right. So I'm going to talk about our Bit 3 project, which is with Lauren, Julie, Brenda, Rhiannon. I changed the order there. And also, I think I'm. Yeah, something. But anyway, as soon as the slide went up, I realized there'll be typos. So what is it that I'm not, I should start with the disclaimer, like all the questions about functor calculus should be directed elsewhere. But I will be talking about doing model categories on calculus of functors. And so what are our objects in study? We want to think about functors from a category C to category D. We can add some adjectives to this functor. Maybe we want it to be a homotopy functor, a simplicial functor, and so on. And usually you want to find the n-excisive approximation of your functor. You want to find degree n approximation. What Kristen was talking about today is what I call degree n approximation in the context of a Boolean functor calculus. Okay, and if you want to compare different calculus of functors, you want a model structure on it where you're, and you want to study your objects up to these approximations. So you want a model structure where two functors are equivalent if their n-excisive approximations are equivalent or if their n-degree approximations are equivalent. So that's what we're trying to understand. So we want to put it, and this has been done. Okay, so you may question what I'm going to do the rest of the time, but I have some names here. I'm not going to read it out. These are the papers that I have looked at, which means there can be several other papers which do also talk about model structures, which I may not have looked at. And do please let me know at the end of the talk if you want some more. So before I go into the kind of things that people have been doing, one thing is whenever I have a functors from a category C to D, maybe C is small or essentially small, there is an obvious model structure that we know how to put on diagrams in a category. So I can think of functors from C to D as some diagrams in D. There is what is called projector model structure, which is like a level-wise model structure. What you can do is you can choose F to G be a weak equivalence or a fibration when at every A in your C, this FA to GA is going to be a weak equivalence or a fibration appropriate. Right? And the interesting thing about this is when D is cofibrantly generated, the model structure you get on fun CD is always going to be cofibrantly generated. For those since main thing that I'm going to care about is this cofibrant generation, and maybe it's not been mentioned so far. Let me point out that having a cofibrant generation means you have way more control on your cofibrations in your model structure, and it's easier to check when something is a fibration. So, and most of the examples that are nice always have this property. Okay, so, but remember I said we want a model structure where I want F to G to be a weak equivalence, then either it's the induced map on the n-excisive approximations or the degree n approximations happens to be a weak equivalence. So this situation, basically I have some functor Q, which is like an endo functor on fun CD, which basically I wanted to have the property that whenever F to G is I will say F to G is a weak equivalence if QF to QG is a weak equivalence. And we can call these Q equivalences. Now, there's this nice setup which was originally done by Friedlander, and then there are several modifications of this. So the version I'm going to talk about is by Gauss-Spiel. And basically, if you start with the right proper model category, and you have an endo functor, which comes with a natural transformation from ID to Q and satisfies these axioms where if something is a weak equivalence already in my model category, then it would be a Q weak equivalence. So it's some sort of a localization that we are expecting to do. And there are a bunch of other axioms I need to check, which I won't spell out. But the consequence is that if all these axioms are true, then you get a new model structure in MQ where the weak equivalences are exactly the Q equivalences, which we talked about before. And you have the same cofibrations. And if you started with a simplicial model category, then MQ is also going to be a simplicial model category. The other extra thing that you get is if your functor is nice with the terminal object, then you also are able to completely characterize what the fibrant objects are in your category. So by Q fibrant, I mean the fibrant objects in this MQ. So for those, if you know functor calculus, then it's kind of clear that this sort of fits the functor calculus situation very nicely, because in all the functor calculus, you have an endofunctor, and it comes with this natural transformation from ID to the functor. Okay. So what is not true is this theorem does not say that if M is cofibrantly generated, then MQ is going to be cofibrantly generated. And that was the main focus of our project. So Biederman and Brodix worked on this in the context of the Billy's homotopy calculus. And they made everything simplicially enriched and showed that after showing that you get a model structure, they showed that actually if D was cofibrantly generated, the model structure they get on functors from C to D is also going to be cofibrantly generated. So what we wanted to do is something similar, but in a way that it applies more generally. Right? So we basically want to do this for discrete functor calculus. And what is discrete functor calculus? I will say more about it in a second, or in 2 minutes. But it is something similar to what Christine was talking about, but in the context of having simplicial functors between simplicial categories. Okay, so it's an enriched version of it. So our setup is going to be the category fun CD, where we're going to talk about simplicial functors with from C to D. And both C and D are, of course, simplicial categories. And the morphisms are going to be natural transformations, simplicial natural transformations. So there are a bunch of things I have to assume. One can check that all the examples that we care about would have this. So C would be essentially small, B would be and would be a full subcategory of a model category, simplicial model category B, and C will consist of objects which are cofibrant in this B. We will assume D is cofibrantly generated, so you can think of top or spectra or chain complexes. And we have some extra assumptions about how weak equivalences, fibrations, and homotopy will behave. Now, the advantage, some immediate consequences of these assumptions is that sequential colimits in D will be weakly equivalent to homotopy colimits. And the left-hand extension of any functor from C to D, like if you extend a functor from C to D to D to D, then that's going to preserve filtered colimits. Okay, so these are some technical things that we need. So Angelica said that we should do one proof. I'm not going to do any proofs, but here's what I think. I'm giving you all the ingredients. So maybe I'm giving you a recipe. Please cook it yourself. Or maybe I'm hiding some secret ingredients. We'll never know. But so what this allows me to do is that in any cofibrantly generated simplicial model category, I have a simplicial fibrant replacement functor. I want to do the simpler, so this was done by Biederman and Rodrigues, but I want to say the simple version of this Q functor that one can think about. So you can think about a functor. What it does is basically, it takes any functor and makes it a homotopy functor, all right? So what this is doing is you take a fibrant replacement of the functor in D, and then you take the Kahn extension, like compose it with the Kahn extension. Then what you're getting, it's not very hard to check because basically every object, I guess after you apply this will be both fibrant and cofibrant, and because you are in simplicial categories, model categories, something which is a weak equivalence will be a simplicial homotopy equivalence. And then again, you use that any simplicial functor preserves simplicial homotopy equivalences, and that will tell you that this functor FHF is simplicial and a homotopy functor. And this can be the simple example that you can check out as we go through the various statements that we make in general for Q. Okay, so it's like a baby case for what we want. So what Biederman and Rodrigues prove is that the category fun CD has a simplicial right proper model structure using Gauss-Fields theorem, in which basically two functors are weakly equivalent if these FHF and GHF induces a weak equivalence, and the fibrant objects are exactly the homotopy functors. Okay, so by homotopy, we have used homotopy functors several times, but by homotopy functors, I mean a functor which preserves weak equivalences. So they start with this model category and then localize it further, again applying the same theorem to show that you get a model structure where two functors are the same if their nx isog approximations are the same. Now, and the fibrant objects in this model structure are exactly nx isog. So the interesting part is that they are able to show that this model, I think there's some kind of, I don't know how to use the pointer, but the cool part of this theorem is that the model structure they end up with is cofibrantly generated. So I noticed this after I transferred the slides. If you're paying attention, I think I repeated the sentence. So everybody was worried about repeating other people's statements. I'm repeating my own statements. But I'm going to say a bit more about discrete calculus because we started off by trying to do model structure for discrete calculus, and then we wanted to do it more generally. So this is something that Christine already talked about. You usually assume D is stable. So the main point is that we want it to be pointed that it has a zero object, and it takes homotopy pullbacks in homotopy. I mean, homotopy pullbacks and homotopy shots are the same, like in spectrum. And this is same as what she defined, but I think she used a slightly different symbol for what I'm using for N. I think this is what Brenda uses, so that's what we are using. But I think this was called PN or in your time.
I think I called it CN, but it doesn't,
Okay.
you're right, it's the same.
Yeah. So what this is doing is basically taking the nth cross effects of the functor, and you basically take the following homotopy cofiber, and this gamma NF gives you the n degree approximation of your functor F, which basically means that it's a degree n functor, and if you apply the cross n plus one functor on it, then you get a point, like weakly equivalent to a point. Okay, so it's an n degree approximation. So one can check that if F is simplicial, so is gamma and F. And what we prove is that in the one has to, of course, check all the axioms, and that's where all the work goes. But what we are able to show is that if you start with your projector model structure on fun CD, then you get a model structure on fun CD where F and G are weakly equivalent if their degree and approximations are weakly equivalent. So in order to do that, so like I said, I'm going to give you all the ingredients and now you can prove this theorem. So the way you do this is you don't actually try to apply Gauss-Fields theorem in the way it is. you modify it slightly. Basically, you note that the axiom E2, which one has to go back a few slides to check what it was. If you know it's true for vibrant objects in your underlying model structure, that's enough. And that will tell you that it holds true for, I mean, this is assuming all the various other things I assumed for my category. So I'm not saying in general this is true. So that M is a slight misnomer, but there are a bunch of things we assumed about C and D, which allows us to do. And the other fact is that instead of checking, if you already checked A1 and A2, you can check this A3 prime, which basically says that a cube preserves homotopy pullback squares, which is much easier to check. And then this will imply axiom A3 holds. So these slight modifications actually makes it much nicer to check. But like I said, our main goal was to actually check, make sure that this is cofibrantly generated. So here's our theorem. So we say that we could apply this, and there is this extra condition that if Q is a functor, Gauss-Field and a functor, that means it satisfies axioms A1, A2, A3, and has this property that it admits a collection of test morphisms, which I'll say what it is in a minute. Then the model structure is going to be cofibrantly generated. Since I'm running ahead of time, I was pointing out to Guy that I really liked his slides because they had these clouds and then we went up to space. And I thought about what I would do for this talk. I would start on the ground, we'd start digging. And then there'd be some concrete, I would start pouring on it. And hopefully at the end of the talk, I would have put up some beams and some structure, and you can build a building out of it. But I wish I knew how to make those pictures, and then everybody would have been more awake during the talk. I'm sorry, I also thought of what I would modify Scott's talk into for this one, but I now suddenly forgot which comic I wanted to think about. I'll get back to it at the end. But okay. This does tell you that I was paying so much attention. All right, so what are test morphisms? If you have any morphism from F to G, and you have a diagram of this kind, so test morphisms for me is a collection of morphisms which have this property that a diagram of the on top is going to be a homotopy fullback square if and only if this following diagram is actually a homotopy fullback square. Now I have to make sense of what I mean by this. So I'm taking some sort of an exponential thing, so some form of x into f, where x is actually a functor from C to simplicial sets, and f is a functor from C to D. Okay. So if you like enriched things, you may want to think about if you take fun CD and everything in simplicial, is your category fun CD going to be enriched over fun CS, where S is your simplicial sets? It turns out it's not exactly enriched, but it has all the nice properties that you would want. So I can do a what Bierman and Roddick's called evaluated potensor. So we use the same language because it is kind of potensor. So we define f to be the exponential thing in the as it's given here as an equalizer, like as a coin, and or a coin. Sorry. The A and B range over these objects, and the nice thing is the model structures interact really well. Okay, so fun CS is a model category in the same as a with projective model structure. Okay, because simplicial sets have the model structure. And one can check that if B is a simplicial model category, then all these statements happen to be true. And if you're used to simplicial model categories, you would see that, or if you're used to talking about model categories enriched over something which is also a model category, then you would see that you would usually expect something like this to be true. So this then allows us to actually create these test morphisms in both the cases. So like I said, I told you, you need to know this. And then if I tell you what the test morphisms are, you should be able to check that these test morphisms actually, so in the first case, when I was talking about putting just making a model category where two functors are equivalent if their homotopy, I don't know, I didn't give a name, but if the HF functor on them induces a weak equivalence, that can be made cofibrantly generated. So for that example, you think of these functors as your test morphisms. And similarly, for the discrete model structure, you use these as your test morphisms. And what we hope is that we can do this more generally. So these are the examples that we have worked out. But one would hope that in general, when you want to apply Gauss-Field skew theorem and you're in some nice situation, then you can actually use these ideas to show that something is going to be cofibrantly generated. I think that's, I don't know. Thanks.
So I don't know, can you give some kind of general picture of what conditions you need on your categories, or what kind of categories you have this excessive model structure for? So if you're like functor from C to D, for what kind of C and D, what do you need to assume for
I
this?
did actually almost state most of it. I provided I didn't miss anything. But C has to be essentially small, and it's like a full subcategory of a cofibrantly generated model category. And it consists of cofibrant objects. I mean, it doesn't have to have all the cofibrant objects, but every object in C must be cofibrant in the.
So topological spaces don't
Yeah,
work.
topological spaces is fine.
Okay.
But C could be like you take,
Okay.
I mean, some sub-collection. I think on D, there's reasonable, nothing like very. I think on D, I'm just assuming it is cofibrantly generated and some nice properties on the weak equivalences and foundation. That's how they behave with sequential elements.
So my question is, I guess similar to the previous one, are there like functors you all were interested in and then like actually showed like functors that we know are equivalent up to this notion? Like in this model structure, like I can't think of functors off the top of my head that are like an excessive equivalent. You guys explored that.
No, I guess, and where you're coming from is that when you want to check if the two, I mean, if you want to check like the two types of functor calculi are sort of giving you the same sort of information, then this is what you would want to do.
Okay,
But not in some specific
okay,
sense.
you can't give me two functors right now that you know, okay.
Maybe somebody else can. I have not made any calculations. There are other things I have calculated, but nothing in functor calculus.
Yes, we thank Rekha again.